Hi, I'm Aditi Reddy. I'm a second year engineering student from Bangalore Institute of Technology. Today I'll be talking about the topic VHDL modules. VHDL stands for Very High Speed Integrated Circuit Hardware Description Language, and it is a language that describes the behavior of electronic circuits, most commonly digital circuits. Now, when I say VHDL module basically signifies a block of code in the VHDL language. So for a better understanding, module basically works the same as it basically signifies the same thing as a function word in a C programming language. So you can have multiple modules in a VHDL code. Now the structure of the VHDL code can be divided into two major parts, and they are entity and architecture. Now the entity part of VHDL, it is the part of the code where we declare all the inputs and outputs of the program. VHDL itself is an case insensitive module, which basically means that using uppercase letters or lowercase letters will not make a difference. So as you can see, for example, the all capital entity and the small lowercase entity will be considered as the same thing. Now, in order to make an entity name or declare an entity name, there are some basic ground rules. The first letter of the entity must be an alphabet, and the special characters are not allowed to be included in a name except for underscore. Except you can only have one underscore at a time, and there cannot be two continuous underscores. The entity name cannot end with a special character. Now, after declaring the entity name, which we do using entity and entity name, as you can see over here, we need to declare all the inputs and outputs mentioned in the code. Now, this declaration includes name, the mode, as in if it's an input or an output or an in-out, and the data type of the input and the output. There are some rules for this declaration as well. Now, while we're declaring the inputs and the outputs, we use a predefined word called port. Now, here, as you can see in the code, we use the predefined word port, and here A. In this example, this code is basically for an AND gate, which is why I've taken the entity name to be AND gate. As you can see, there's only one underscore. Now, this code has two inputs and one output. So A here is an input of data type bit. Bit basically means that it's of binary value, it's either of 0 or 1. Now B is also an input and Y is an output which is of mode type out, and the data type is also bit. All of them are of bit data types. Now the certain rules for declaring these inputs and outputs are every declaration of every variable must end with a semicolon. Now the port name and data type for every declaration must be given. You cannot put only A and not declare its type, its mode or its data type. And at the end, we need to end the entity. So end entity and the semicolon. Now the architecture part of VHDL. This is the part where we declare the relationship between the inputs and the output. Now we can write more than one architecture for the same entity. The architecture is a predefined word. The word architecture is a predefined word. Now, the syntax of architecture is the predefined word architecture and the architecture name, which you can write as per your will, of the certain entity name, because you can have multiple architectures per each entity. So you will declare what entity the architecture belongs to. The entity name is what you have declared in the previous part of the code, which is the entity part. And then you have all the declarations of the architecture, and you use the keyword begin to begin the architecture body, in which there will be statements which you will be executing as the variable values change. And in the end, we have to end architecture with architecture name and a semicolon. Now, for example, let's take the NOT gate. As we all know, NOT gate is a gate with only one input and a complemented output. Now, let's say F is the output and A is the given input, then F is equal to A bar. So in the in the truth table, we can see that the input A, when it is 0, the output is 1, and when it is 1, the output is 0. Now, looking at the VHDL code of a NOT gate, we have declared the entity. I've taken the entity name to be not G for not gate. So entity, which is a keyword, entity not gate is. We use the keyword predefined word port, the input A, which is an input and of bit data type, and F, which is an output of bit data type. And now we end the entity, that is a semicolon at the end of every declaration. We end entity, which is the same as the entity name not G. Now coming to the architecture part of the VHDL code. Architecture, Not arc of not G is you begin. Not arc is the architecture name that I have taken here, and of not G, which is the entity name, is we use the keyword begin. F less than equal to not A. This ends with a semicolon and end not arc. Now let's take another example, such as this circuit. In this circuit, there is an AND gate with two inputs A and B. The output of this AND gate, which is C, acts as an input along with D for the next OR gate, and whose output is E. Now, looking at the VHDL code, the entity part of the VHDL code, sorry, this part. So I've taken the name of the code to be name of the entity to be two gates because there are two gates. So entity two gates is port. Now, when there are multiple inputs of the same data type and the same mode, I can declare them all in one sentence with a comma between all of them. So now I have A, comma B, comma D, which is A, B, and D as the input data type of input mode of bit data type, and here E is the out data type, out mode bit data type. Now C shall be declared later in the architecture part, as it is neither input nor output, it's an in-out type. Now the end entity two gates architecture, I've taken the name of the architecture to be gates of the entity name two gates. Now we take another variable signal, which is an intermediate variable. So here C is an intermediate variable. So signal C is of bit data type. Sorry. Yeah. Now here under in this code, the code lines fall under the architecture part, which is the architecture body, is C less than equal to A and B, and E less than equal to C or D, where A and B are ANDed here and C and D are ORed here. Now these two statements are called the concurrent statements, which basically means that these two statements are the first statements to be executed when the values are changed. Now we end the architecture, so end gates, which is the name of the architecture. Now, Vhdl adder. Now, as we can see, this is a full adder which has three inputs, X, Y, and the C in. And we have two outputs, that is C out and the sum. So this is a carry in and this is a carry out for a full adder. Now, let's look at the VHDL code. Entity full adder is, I've taken the name of the entity to be full adder, port, the inputs X, Y, C, N of in mode bit data type, and C out and sum of out type bit data type. Now end entity name full adder. Architecture, I've taken equations to be the architecture name. Of course, this can be varied according to as per your wish. Now, architecture equations of full adder, which is the entity name, is begin sum less than equal to x XOR y XOR cn. As we all know the code of full adder, these three are XORed, and which results in the sum. Now C out is xy or xcn or ycn, which means x and y are ANDed, x and cn are ANDed, y and cn are ANDed. Now these three are ORed again after 10 nanoseconds. Now we end equations. Now, coming to a 4-bit full adder, a 4-bit full adder performs the addition of two 4-bit binary words. Now, there are three inputs for a 4-bit full adder. 4-bit full adder is basically a combination of four full adders. Now, there are three inputs, A, B, and Cn. Let me show you the circuit, the diagram of 4-bit full adder. As you can see, there are four full adders where the first full adder has three inputs, A0, B0, and C carry in. Now the carry output of the first full adder acts as the carry in input for the second full adder, which again makes it have three inputs, A1, B1, and C1. And similarly for the third full adder, where C2, which is the output of the second full adder, acts as the input for the third full adder. And similarly, in the end, we have the output CO, and every full adder has two outputs, S0 and C1, which acts as the input for the next full adder, which in turn has S1 as its output and C2 as its output. Now coming to the code part, entity adder 4. I've taken adder 4 to be the name of the entity because there are four adders. Entity adder 4, port A, B, which are of input type, and they're of bit vector type 3 down to 0. As you can see, it's A3, A2, A1, and A0. Now this is 3 down to 0. If I had written 0 to 3, it would have been A0, A1, A2, and A3. So 3 down to 0. And the carry in, which is an input bit. Now S, which is an output bit, which is again 3 down to 0, 3, 2, 1, 0. And again CO to as the output bit. Now we end the entity, which is end adder 4. Coming to the architecture part, I've put the image here again. Coming to the architecture part, architecture structure, I've taken the architecture name to be structure, and of the entity name was adder 4. So architecture structure of adder 4 is, now I've declared a component here because as you can see, each full adder acts as a component. So there are 4 components here because they all do the same function. So I can just make them all common and put them all under one component and just call the component every time I need a full adder to function. So I've taken a component full adder, port XYCin. We know the code of full adder over here. XYCin in bit, C out sum out bit. I've just put this code under the component part in order to keep calling it. So as I've told you, you can use modules, then modules, like multiple modules, and they will function as a function in a code. Now you can have XYC in bit, C out sum out bit. So 3 inputs, 2 outputs, you end this component, and I will explain the signal C a while later. Now we begin the code, and we have taken 3 full adders, full adder 0, full adder 1, full adder 2, full adder 3. I'm sorry, not 3, 4 full adders. Now full adder, I'm calling the component, and port map is a predefined word that I can use to call this function, this component. So using port map, I can access this part of the code. So full adder, port map, these are the 3 inputs, A0, B0, Ci, and C1 and S0 are the outputs of the first full adder. As you can see, A0, A0, B0, B0. Ci is the Ci. C1 and S0 are C1 and S0, the outputs. So this is for the first full adder. Coming to the second full adder, I access the same code, but I change the inputs and the outputs. So it is A1, B1, C1, C2, S1. Similarly with the third full adder and the fourth full adder. For the fourth full adder, A3, B3, C3 are the inputs, and CO, which is the C output, and S3 are the outputs. Now, in between every full adder, there is another component C1, C2, C3, which acts as the intermediate vectors. So signal is used to declare the intermediate variables, which is C. So signal C bit it's of data type bit vector 3 down to 0, as there are only 3 down to 1, as there are 3 variables C3, C2, C1. Now the uses and advantages of VHDL. VHDL is used for multiple purposes. It's used for describing hardware, it's used as a modeling language, it's used for a simulation hardware, and like multiple other uses. Now, there are many advantages of VHDL. It provides a very flexible design language. It allows detailed implementation. It supports various design methodologies like top-down approach and bottom-up approach. It supports all CAD tools. It strongly supports code reusability and code sharing. So it makes it very helpful to use it for designing electronic circuits. Thank you.